Hope you're all awake and alert. Okay, so we are discussing Map Reduce. So this was started within Google as a way to process very large amounts of raw data. This data is so large, it must be distributed across not a few machines, but thousands of machines. The distribution implies parallel computing since the same computations are performed. So you are doing the same computation, but you want to do it on large amounts of data, so you can piece it, partition it, and cut it into shreds and do it. MapReduce is an abstraction that allowed Google engineers to perform simple computations while hiding. So, as I said, this is important because earlier way of doing parallel processing required a lot of learning from the people who are involved. They tried to take most of that away from the end user. So, to summarize, MapReduce is a data parallel programming model that uses clusters of machines. Remember, we talked about grid computing and cluster computing in the cloud context. Most of the MapReduce work goes on in clouds. Pioneered by Google, at some point they were able to process 20 petabytes of data per day, popularized by, so even though Google, surprisingly, Google developed this MapReduce, the publicly available version today was developed by Yahoo. So we call it Hadoop. So it is developed by Yahoo, and it's publicly, Google for some reason did not want to make their system available for public. So what do people use MapReduce for? At Google, they use it for index building, article clustering for Google News, statistical machine translation. At Yahoo, same thing. Index building is a very data intensive job because just imagine what is index building. These crawlers collect words from every web page, then do the stop words and other things, and then they index them. That's why when you give a bunch of words, they take all the web pages for each word and do an intersection of the web pages and give you the one that has all the words. At Facebook, it's used for data mining, ad optimization, spam detection. But what I have put in the sidebar is very important. Note that most or all of these applications are quite different from the traditional DBMS application. So they are not the same. Very large data sizes, very importantly, one-time computation. That means in a DBMS, you are asking the same queries every often. So if you are doing a employee management or payroll management or student management, you are asking the same queries. Here it is not. You do the log analysis once, then the new data set comes. You do the same analysis on the new data set. Then another data set comes. So you don't do the same analysis on the same data set. Versus data storage and management. So the main difference between database management systems and MapReduce is one is customized or tailored for data storage and management, whereas in MapReduce, data storage is there for intermediate computation, but there is no data management per se. You're not asking queries. You're writing a program to compute something. In that way, this may be similar to the traditional mining of doing one thing. SQL is not a good vehicle for doing this kind of task. Defining schema and loading this data into DBMS. So imagine if you have to load large amounts of data and do only one-time computation, again load another set of data and then do a computation, it's a waste of time and resources. So this model is very different from that. So what you have to understand is, it is not MapReduce or DBMS. You can have both. Each one is used for a different purpose. So it's not one or the other. That's important to understand. And more importantly, if you want to use a DBMS, you have to define a schema. You have to load the data, and then you have to ask queries and generate reports. Here, there is no need to define the schema. There is no schema. Whatever format that you give that data in, your program will understand and take care of it. So schema creation and loading the data is a complex process. If you do that, you want to amortize that over a very long period of time. You don't want to do it for one execution or one query. So that's very important to understand. It's also used for graph mining. We are doing it. It is used for page rank calculation, machine learning algorithms. Today, almost all machine learning algorithms have been translated to Map Reduce version to make it faster, response time, shortest path. Problems are being ported to Map Reduce on a daily basis. It's a very popular research area, and porting algorithms into Map is not always straightforward. So this is where the challenge is. It is not that you can take an algorithm and just convert it into Map Reduce. There is a lot of design that goes into it. Sometimes the algorithms are somewhat different from what you are doing. In research, Wikipedia conflicts are being analyzed using this. Natural language processing are being done. Bioinformatics, astronomical image analysis, ocean climate simulation. We are using it for graph mining. We are using it for multi-layer network analysis. We will see that in the next lecture. So, MapReduce design goals are scalability. That's one of the things we wanted to emphasize in this course is, why do we need scalability and who can give you the scalability that you want given the sizes of the data. So large volumes, hence focus on data parallelism. I mean, these are just numbers, scan. If you have 100 terabytes of data, if you use one node at 50 megabytes per second, it takes 23 days to process it. The same data can be processed on a 1000 node cluster in 33 minutes. This is what scalability gives you. It doesn't change the amount of computation you need to do. You still need to do the same amount of computation, right? Because the data size is large, but you are doing it in parallel. That reduces the response time. So understand clearly the purpose of parallel processing is not for reducing the amount of work, but for reducing the total time it takes to do the job. It is the same principle as if one person is working on a project and you put 4 more people, you may be able to finish it faster. But still, everything has to be done. Cost efficiency. This is where the commodity nodes come into picture that I spoke about. These are cheap, but they are not reliable. Commodity disks. So these are CPUs, cheap, and RAID makes them reliable. So that's very important to understand. Commodity network. So they incorporated automatic fault tolerance, meaning fewer administrators, easy to use, fewer programmers. So these are the highlights or design goals. So MapReduce does automatic parallelization and distribution of data. It also supports fault tolerance, but the kind of fault tolerance supported by MapReduce is somewhat different from what a DBMS does recovery. Provides status and monitoring tools. It's a clean abstraction for programmers, borrows from functional programming. Users implement 2 functions, only 2 functions. That is what makes it very attractive and useful. So what are those 2 functions? One is called the map function. The other one is called the reduce function. That's where the name comes from. And the map function, this is important to understand, takes in an input value. So every input to map program should be in the form of a key and a value. The value can be anything, the key can be anything. The value can be as big as you want, it can be an entire object, and the key can also be null. And it takes one key and the associated value and converts it into maybe a different key called the intermediate key and a list of values. So this is also important to understand, that a single input may be converted into one or more outputs. Now, this output is fed into the reduce program. Intermediate key and intermediate value list, and then this reduce program produces the final output in the form of the output key and output value list. That's it. That's what map reduce is. Now you know everything about map reduce. Just write the map function, write the reduce function. Input key, intermediate key and out key need not be the same. They can be very different or they can be the same. So in a nutshell, the end user writes only two functions or two methods. All other things that happens in between are managed by the underlying framework. Any questions? So just to give you an idea, this is what a server forms look like. It may contain servers up to 10,000 servers and more. I was in Sweden a couple of years ago, in the northern part of Sweden, and my host told me that there is a Facebook server farm 50 miles north of that place. So we were driving to see something and we went there. So this was a server farm by Facebook that was fenced. It was 1 kilometer by 1.2 kilometers. And there was a huge building which contained, I don't know how many servers, maybe 100,000 servers. So my question to you is, why does Facebook go all the way to Sweden to set up a server farm? Is there a reason? Anybody?
Temperature. Temperature.
Temperature, exactly. So when you have CPUs, they generate a lot of heat. When you have 10,000 CPUs, 100,000 CPUs, they generate a lot of heat. They need a lot of air conditioning. But in the northern part of Sweden, it is cold most of the times. They don't have to spend any money for air conditioning. There is natural air conditioning, they just have to let the air in. That's all they have to do. So most of these people go and set up these huge server farms that generate a lot of heat in cold climates because they save a lot on the electricity and the air conditioning. So if you want to understand map reduce, now I've been teaching this course for a long time and I have sort of revised and changed slides many a times. So you need to understand it at 3 levels. You need to understand it at job level, and then we'll see the other two. So what is job level map reduce? You have to configure a map reduce job to run it on desired number of mappers and reducers. So when you create a job, not the program, when you create a job, you need to say how many mappers do you want to use, how many reducers you want to use for this particular job. Now this is purely up to you. You may use 10 CPUs, you may use 100 TPUs, you may use, but the cost varies. Remember the rental model, pay-per-use model? Because of that, the more resources you want to use, the more you have to pay. It depends upon your affordability and what kind of response time you want. Also, you have to provide something called block size for sharding. I'll come to that. Then you have to understand or decide whether you have a single input file or whether you have multiple input files. Because if you have a single input file, then you write one map program for that file format. If you have three input files, the formats may be different, so you may have to write 3 map jobs. But each map job can run on any number of processors. So first file can be sharded and processed on 10 processors, second file may be processed on 100 processors, third file may be processed on 50 processors. So you have to determine the total number of mappers and how many mappers you are going to use for each input. Decides number of mappers methods to write. So this determines how many mapper methods you have to write. Unless the files are identical, then you don't need multiple inputs, right? You can just combine them and use the same thing. Whether a single job or you need to use chained multiple jobs. In this jargon, a single job means one set of mappers and one set of reducers. Together make up a job. So a job is map, reduce, pair. Any number of mappers, any number of reducers, you decide. But some of the problems cannot be solved with one map, reduce, pair. You may need a second pair, you may need a third pair. So you need to decide that. That is called chaining. So you feed the output of the first job into the second job. You feed the output of the second job into the third job and so on. So that's what is called. The other, so data flows from one job to the other. The other one is whether it's an iterative algorithm or a one-shot algorithm. If it is an iterative algorithm, then you may have 2 jobs. The output of that goes back to the first job, keeps doing it till a stopping condition. So iteration is different from chaining. They are not the same, but you need to understand what category your algorithm belongs. It can be just a straightforward chained algorithm or it can be an iterative. So many algorithms like PageRank, graph mining that we do are iterative algorithms. Other issues such as reading other files in the mapper or reducer is important. Many times in addition to the input file, you may need other auxiliary files that are used by the mapper and sometimes by the reducer, so you have to make sure you provide that. So this is what I call understanding of things at the job level, so higher level. Then you need to understand things at the map reduce level, map function level and the reduce function level. What are they? The code that you write and its understanding as well as conformity with the paradigm. So you have to write some code. So you have to write map code, you have to write reduce code. So you have to understand how you should write it with respect to the input and the paradigm. So the mapper code consists of one or more based upon the number of inputs. It has a setup part, main part and cleanup part. In the setup part, you do things like initialization, reading files, setting up instrumentation, creating data structures used during the main part. Main part is the actual main function that you write, code for your application, and then your cleanup part is to writing additional files, instrumentation, etc. So every map function can have these 3 parts, but setup part and cleanup part are optional. You may not need that depending upon your algorithm. You may just have the main part. Same for the reducer code. You have a setup part, main part and a cleanup part. There is something called a combiner. It's optional. If you want, you can write a combiner and this combiner will be executed after the map method is executed. So combiner will always be executed after the map task. Writing intermediate results and computation if any between it. So if you are chaining or if you are doing iteration, You may want to do some additional computation like merging files and other things in between two jobs. That you have to do separately outside of the MapReduce framework. You have these files, then you can do whatever you want with that, and then you feed it into the next batch job MapReduce. So is this clear what you nearly do? Then there is the framework. So job level, MapReduce level, framework level. So what is the framework level? Here, a lot of things are done by the framework and it is transparent to the user. That means the user does not have to write any code for that. But you have to understand it. You have to understand what the framework does. Because if you don't understand what the framework does, you won't be able to write your mapper code or your reducer code. So first thing you have to understand is how are shards created and splits handled by Hadoop. So what is the meaning of a shard or a split and who creates it and how it is handled. How are multiple mapper nodes used for the same input? So if you have multiple mapper nodes, how it is used. Feeding input to the mapper node, one key value at a time. It's always one key and one value at a time. You cannot feed more than one key and more than one value to the mapper at the same time. Because you don't do the feeding, the framework does the feeding. And it will always feed one key and one value. Processing at the end of the mapper code on the mapper output. So framework does a bunch of processing after the map method is run on the output of the mapper. So you need to understand what it does, how it does, and why it does. Processing at the end of the combiner code, if there is one. So at the end of mapper, there is something that happens. If there is a combiner, something happens at the end of the combiner. Partitioning and who does it. So there is this notion of partitioning. This partitioning is different from shards or splits. So they use a different word not to confuse one with each other. We use partitioning very loosely many a times, but here data split is different from the partition done by the framework, and there is a difference between them. Why is sorting and grouping needed and who does it? What is shuffle? There is a process called shuffle. Principle behind the shuffle includes exchange of data between mappers and reducers. So shuffle name came from this. So once all the mappers finish their task, the output of the mappers need to be sent to the reducers. And then reducers do the second part of the job, and then you get the output or fed into the next job. Now you need to understand how this transfer of data from mapper output to reducer input takes place. That's a very complex process that involves sorting, that involves merging, that involves partitioning, and then shuffling, meaning each mapper sends it to different reducers. Which partitions from the mapper are sent to which reducer? Understand the difference between a mapper task and a mapper node. So this is also important to understand. A mapper node is a physical resource, like a CPU or a core. A mapper task is a logical computation. So you always run a logical computation on a physical resource. You may have more logical computations, less number of physical resources, then you do it sequentially. So if I have 4 nodes and 8 splits of data, I can only run 4 at a time. So I run the first 4. When they are finished, I run the next 4 on the same nodes. It takes more time, less parallelism, but it costs less. Each mapper task runs on a mapper node, process or resource. So understand the difference between a task and a node, a resource and a logical execution of a task. Any questions? Without clearly understanding all the three levels, I think you will not be able to write meaningful MapReduce algorithms, much less code. Again, I have to make a distinction that it is useful to write algorithm first and then translate that into implementation. What I see many times our students do is, when I ask them to solve a problem, they start coding it directly. And then I ask them, do you have an algorithm? No, sir, I will develop the algorithm as I code. So this is a very standard technique used by most of you, and that is a very bad practice. You cannot write a code if you don't know what you are writing the code for. You cannot just develop the algorithm on the fly unless it is a very basic algorithm. Add 10 numbers, of course you can write the code. But compute a prime number, you cannot write a code directly because you don't know the algorithm for identifying a prime number. First you need to figure out the algorithm and then code. So a lot of students waste a lot of time writing code, and then it doesn't give the answer they want, then they go and change the code. So they do what I call exhaustive programming. Not extreme programming, exhaustive programming. That means trial and error. Change this, see whether you get the result, change something else. To me, this is more like a lot of monkeys using a typewriter and generating Shakespearean play. That is never going to happen. So don't write your code till you have an algorithm that you have verified, that is correct, that you have tested. Then the total time taken will become very less. The fact that many machine algorithms have been successfully translated to this is indicative of its utility and capability. Although paradigm seems very simple, user written code is typically not very big. Considerable amount of heavy lifting is done by the underlying framework, hence need to understand it, freeing the user to focus on the problem. So you need to focus on your problem, not other things. So a little more detail. Input is a set of key value pairs, KV, K can be null. When I say a set, it's a list of sequence. It can be whatever size. You may feed 100,000 key value pairs, 1 million key value pairs, or 10 million key value pairs. It doesn't matter. User supplies two functions, as I said, map function, which generates some output, converted into something, and then reduce function takes that, generates the output. If you want to understand it pictorially, this is how it happens. So you have an input file. We have a very large input file. Let us say you have an input file that is 200 gigabytes. Now you shard this file into input split. So you can say 200 gigabytes, let me split it into 500 megabytes. So I don't know, you may generate 40 splits. So you are going to process each split individually. So you have parallelized it, if you want, in 40 possible ways, but depending upon how many mapper nodes you choose. So if you have 40 splits, 40 mapper nodes, it gives you maximum parallelism. If you have 40 splits, 20 mapper nodes, then you have to, each mapper node has to process 2 splits sequentially. So these input splits, each input split is fed into a mapper task. Remember, I'm not saying mapper node because mapper tasks run on mapper nodes. And they convert map KV to K prime V prime, where V prime is a list. And then the magic happens here. This is what we call shuffling. And in this, it does a lot of things. Part of shuffling happens in the mapper, part of shuffling happens in the reducer. In the process, it does sorting, it does grouping, and it does partitioning. And once all of it is done, then it goes to the reducer. It goes to the reducer node, and then output file you get. So this is what happens. So number of mapper tasks depends upon the number of input splits. Number of mapper nodes is user defined. And the system will make sure all the splits are run on the number of mapper nodes you give. If you use one mapper node, then it becomes a single CPU processing. That means all the splits have to be processed by the same mapper node sequentially, then the response time will be very long. So how do you handle data in Hadoop? It uses a special file system called HDFS. This is Hadoop distributed file system, which is different from network file system. You guys may be familiar with network file system. Network file system is used to access data over the network. Now, although every CPU, every commodity unit has its own local disk, you can also access data from some other disk that is visible to you using the network file system. So you can ask for data on some other machine to do that, but Hadoop developed its own thing for some reason. I'm going to sort of skip some of these things because I have a lot of stuff to cover. So what is Hadoop distributed file system? Files are split into either 64 megabyte blocks or 128 megabyte blocks by default. But you can also specify the size. You can say, I don't want 128 megabytes, I want 500 megabytes. And that's fine. So every parameter that is used in Mapper can be customized by the user at the job level. And blocks are replicated on at least 3 different nodes. Here we have shown 4. 3 nodes are common. Single name node is used to store the metadata. This node knows which are the machines or the places where the data is stored and how they are stored, whether it's RAID 0, RAID 1, RAID 2, RAID 3. So if one of these things fail, then the data is reconstructed from the others and the processing continues. Single name node metadata files names block. Data is stored on multiple data nodes, optimized for very large file sizes, sequential reads, because you're reading chunks of data and feeding it. So remember, even though we say it is split, the physical file does not actually get split. What the split is to say, this split starts from this byte to this byte, next split starts from this byte to this byte. So if you say read or take split 5 and do it, then it knows where to read from, where to end and process. So physically, the files are not split. HDFS can store large amounts of data, gigabytes to terabytes to petabytes, is spread over several machines, much larger file sizes than NSF. It stores data reliably using RAID. If individual machines fail, data is still available. It provides fast, scalable access to this information, and streaming access integrates well with Hadoop Map Reduce, allowing data to be read and computed upon locally when possible. HDFS is not a general purpose NFS. Performance is good, some of these are not very relevant. So the entire Hadoop system is implemented in Java, including HDFS and so on. So it uses TCP/IP and RPC underneath. So let me see. So input files and charts. Application input file need to be on HDFS. So first thing you need to do is to load your file, however large it is, onto where you are running your Hadoop or a Hadoop system. Mostly it's a cloud, so you have to upload it into the cloud to do that. Input file assume it to be very large. A block size can be provided to shard the input file. So once you provide the block size, Hadoop system will automatically split it into whatever number of chunks it becomes. A default block size will be used if none provided. The input file is sharded based on the block size. User can control the number of shards by changing the block size. Based on resource used and affordability, each shard is considered an input split. Each input split is processed by a mapper task. Each input split is processed by a mapper task which runs on a mapper node. Number of mappers as well as reducer nodes can be specified by the user for each job. So if you have multiple jobs, job 1, job 2, job 3, you can specify the number of mappers for job 1, reducers for job 1, number of mappers for job 2, reducers, so on and so forth. File is not split. As I said, splits are calculated and stored in the name node. Offsets are calculated and stored. So this is the overall architecture of a map reduce. So there is a master node. This is very important. User program is sent to the master node. Master node determines and controls everything else from that point onwards. Master node is responsible for allocating the mapper nodes. So if you have indicated 3 mapper nodes, it will allocate 3 physical resources or CPUs for executing the mapper tasks. Now if the number of splits are more than 3, you can see that this map node processes split 0 and split 3, whereas this processes split 1 and split 2. So that's how it determines how to process all the splits with the given number of mapper nodes. Okay? Once the mapper nodes compute, they write their output to a local disk. These are local disks. Then the map master allocates the number of reduce nodes. Now remember, number of reduce nodes need not be same as the number of mapper nodes. And then it also tells these reducer nodes which data to take from where. And then the reduce nodes take that data, do their work, and then write the output. So this is at a very high level. So this is what happens. Now this does not show what happens in between mappers and reducers. It assumes that all of that happens and the reduce nodes will automatically somehow know where to get the data from and what to do. So this is how it is. Now this master node is the one in control. So it keeps pinging these nodes periodically. It uses a timeout mechanism. If a worker node does not respond for some amount of time, it assumes that this node has failed and it allocates a different node and then asks it to recompute for that split. So this is how fault tolerance is done. So the master node is responsible for making sure that individual node failures will not affect the computation that you are doing. Same thing for the reduced nodes. It will do the same thing. So map node failures and reduced node failures will not affect the completion of the job. The only time a job completion can be affected is when. When can happen in this scenario? Anybody? What happens if the master node fails? If the master node fails, then that job cannot be completed. because master node is the one that is responsible for the execution of the job. If that itself fails, then there is nobody to recover that. So then it indicates to the user that this job has to be restarted. So there is a failure, single point of failure, only for the master nodes. All other points of failures are considered. Disk failures are taken into account, mapper node failures are taken into account, reducer node failures are taken into account, but there are no multiple masters. There is only a single master in the Hadoop environment. So keep that in mind. So job execution, the master initializes the data and splits it as specified or based upon the given or default block size, sends each worker its partition or split task, receives the results from each worker. When we say receives, it doesn't get it physically, it gets its location, where it is stored, and some meta information. Then the worker nodes receives partially split, actually its location from the master, perform the processing and notify the master when completed. So that's how the processing takes place. So master node controls the execution of all the splits by the master nodes. When it is done, it initiates the reducer nodes, and then once it is done, it completes. So, but all this happens behind the scenes. The user does not have to worry about this. Coordination, master data structures, it pings for idle, in progress or completed. Idle tasks get scheduled as workers become available. When a map task completes, it sends the master location and size of its or intermediate files, one for each reducer. So remember, number of mapper nodes is different from number of reducer nodes. If there are R reducer nodes, minimum is 1, maximum can be whatever you want. It creates R intermediate files, one for each reducer. Master pushes this into the reducers. Master pings workers periodically to test failures. It uses what is called a static load balancer. That means it doesn't take the dynamics of the network and other things into account. So clarity on map reduce. User can specify the number of splits. We said that. Independently, number of mapper nodes can be specified. A node corresponds to a processor and a task is run on a processor. Number of reducers can be specified independently. Hadoop will create R partitions, output for mappers and send them to them. Number of mappers and reducers can be determined independently, but it is usually not arbitrary or a head-up. So the user should determine how many mappers do I need for this job? How many reducers I need for this job? It is not that everything, I mean, you wish that all of this is done automatically by the system, but there is no way that it can know. Number of mappers and reducers can be, but they are determined based on the amount of computation to be done and dividing the computation among the mappers, or for experiments to understand. So how do we do that? So suppose say the mapper, for each key value, suppose it generates 10 outputs. Then the output size increases by 10-fold at the end of the mapper processor. Then it does a lot of other things. Now you have to take that into account to see how many reducers you need to process it. Or if the mapper does not blow up the output space, then you don't need many mappers. Or if the mapper reduces the output space, then so you need to know, because you are writing the map program. You know what it does. Hadoop system cannot know what it does. For it, it's a program. So this is what happens. You have the large amount of input data. Node 1 gets a slice, node 2 gets a slice, node 3 gets a slice. What happens in the mapper? Map code method takes an input key value pair and generates 0 or more. Mapper processes one key value pair at a time. Does not. This is important to understand. There is a circular buffer in the mapper. So when it outputs, so remember we are dealing with very large data sizes, and the assumption is all of the input or all of the output cannot be stored in memory. If we can store everything in memory, we don't have a problem. We don't need parallel processing. We can just load everything into memory and run it. So this circular buffer in the mapper, when it reaches a threshold percentage, 80%, it is put into a disk. Each spill is partitioned and a group by is done on that, and all values for the same key are grouped. All values for the same key are merged, creating a value list. Number of partitions is equal to the number of reducers specified defaultly. This is done for each spill, as there can be many spills by a mapper task. Each spill corresponds to a buffer size. At this point, the mapper has n partitions for each spill, and then it does the same thing for all of them. So, I wish I had more time to explain this a little bit better, and also usually I go through a concrete problem and show how to solve problems, but unfortunately in this course we don't have that time. In fact, Map Reduce itself can be a course for 1 week if you really want to understand all the details. Map method function written by the user is executed by each instantiation of mapper task. All the key value pairs output by the mapper are partitioned, sorted. So this is what happens in the transparent phase by the framework. So you don't have to, because sorting is not easy, especially sorting on the disk is complicated, grouping is not easy, and then merging is not easy, partitioning is also not easy, but all of it is done by the system. As I said, if you have a combiner method written by the user, it can be executed after the map function. The output of combiner is merged to a set of key value list, and this value list is what is sent to the reducer. So mappers are separate, reducers are separate. There is a network that connects them, and the shuffle sends data from all. Actually, it doesn't send the data physically. It tells the reducer, take data from here from the network. Each reducer processes its partition. Reducer always writes output to the HDFS, whereas the mapper does not write the output to the HDFS, but writes it to the local disk. So this is what happens in the mapping. As I said, each key value record is sent for processing separately, and this is this is the hello world equivalent of map reducer programming. Here we are counting the number of characters, number of letters. In the input, how many A's are there, how many B's are there, how many C's are there. So these are 4 mapper nodes, let us say 4 splits. A first mapper produces this 1 A and 2 B's. Second mapper says, I have 3 C's and 6 C's. This one says this. Now if there is a combiner, it will merge these two. Here there is no merge. Here, since both are C's, 3 plus 6 is combined to 9. Here there is no merge, here there is no merge. Now this is partitioned, sorted, and you send to the reducer. There are 3 reducers, so A comes, every A from any mapper comes to this reducer, B comes to this one, so A from here comes to this one, A from here comes to this, so it becomes A15, B from here comes to this, C from here, C from here, C from here comes to this. So each reducer processes this one. finally it outputs and says there are 6 A's, 9 B's and 19 C's. So, sorry for the hurried explanation. It does take more time to absorb this concept and to understand it clearly. So what happens in the mapper? If a combiner is provided, it's executed on partition. So I'll skip some of this because this is useful, but because I need to give at least. So this is what I said, partition sort. So here is the input split, here is the map task, here is the buffer, here are the spills, and this is where it creates partitions for each spill, and then it sorts and merges, and then it sends one partition to reducer 1, another partition to reducer 2, another partition to reducer C. Similarly, from other tasks, you get one partition to this reducer, another part. So this is what happens. So corresponding things from every mapper comes to the same reducer. Reducer 1, reducer 2, reducer 3, depending upon how many reducers are specified, and then the reducer knows what to do. Now the reducer runs your program, the program that you have written. What happens in the reducer? So shuffle sends, remember here, by the time it comes to the reducer, it's not key value, it is key value list. It's a set of values for that key. To each reducer from different mappers. How is that determined? This is based upon a reducer reads the same numbered partition from each mapper. Each reducer merges the value list of the same key, formulating a global key value list, and then it applies the reduce function also returned by the user. So remember, this is what you write, map code is what you write, everything else is done by the framework. This is what I said, transparent to the end user and happens as part of the framework. It operates on one key value list at a time and puts the output on the HDFS. So this is a little bit another picture showing the shuffle. So you can see that every mapper sends part of the information to reducer 1, part of the information to reducer 2, part of the same thing here. So this can be a complete graph. Think of mappers as nodes, reducers as nodes, and the connectivity as an edge. So this is a complete graph, exchange of information happens. Reducer, so the name reducer comes because it is doing aggregation. Mapper name comes because it is taking an input and mapping into one or more outputs. So it is mapping, reducer is reducing, which means it takes the entire value list and then reduce it to the proper output. Whatever function it wants to apply. If it wants to do the average, it can do the average. If it wants to do the max, it can do the max. It can compute the median. Whatever it is, it can apply. It can also do complicated things. So, I have a set of slides to test your understanding. I think I'm going to skip that because it is going to take a long time. So input-output locations, input that you provide and final output are always stored on HDFS. Scheduler tries to schedule map tasks close to physical storage. So this is an optimization that is done by the Hadoop framework. Intermediate results are stored on the local storage. Scheduler also tries to schedule reducer tasks. So if the output of the mapper is stored in some node, the reducer node will be closer to it because data read will be faster. If it is very far away from this node, then it takes more time to read it. So there are local optimizations. Output of job is often input on a job. Not all problems are solved. So fault tolerance, I think I already discussed it. Map worker failure, it is restarted. Reducer failure, it is restarted. Master failure, map reduce task is aborted and client notified. How does this compare with recovery in DBMS? Will not do that. So map invocations are distributed across multiple machines by automatically partitioning the input data into a set of splits or shards. The input shards can be processed in parallel on different machines. Each shard becomes a mapper shard. Each shard are split. One mapper processes one shard at a time. Number of mapper nodes need not be the same as the number of splits. Then multiple splits are processed on the same mapper node. Reduce invocations are distributed by partitioning the intermediate key space, groups using partition functions. Number of reducers can be specified. By writing your own partition function, you can do that. Now, there is an option in Map Reduce to substitute everything it does as part of its transparent jobs by your own custom code. But you have to become an expert Map Reduce programmer in order to avail those facilities and do those things. So I'll skip testing your understanding. I assume you have understood everything very clearly. You may want to just go over this if you want, because so overlap of shuffle. I think this is another concept that you should understand. So initially we said that all the map jobs should complete and then the reduced jobs will start, but that is not really true. Exchange can start before the map jobs are complete. So suppose say you have 10 splits, 5 splits are complete and the other 5 splits are being executed. Now the data from these 5 splits can be sent to the reducer. So by doing this, you are overlapping shuffle and map processing. Shuffle and some reduce processing, this will further improve the response time. So that is what this slide is saying. There can be overlap of shuffle. This process of moving map outputs to the reducer can overlap with other map tasks, what the reducer does transparently, and this is useful. I'll skip this. So we'll try to wrap this up in the next few minutes. So how does you as an end user program Hadoop? So it's you and there is the Hadoop cluster. So typically you access it over the network and you have to log into that system and then you get a login, you get some space, you have to upload things into that one and do that. So you first load your data into HDFS. So there are scripts for doing that and then you develop your code locally. So you can develop your code on your laptop. In fact, you can also install Hadoop on your laptop. There are Hadoop installation and then you can test your code on your laptop first. Once you are convinced it is running, because your laptop does not have a lot of resources. You cannot say I want 100 mapper nodes. But once you think it is running correctly, the output is correct, then you can even test it on a smaller amount of data as sanity check. When it is running, then you can give the full size data onto the cluster and do that. Then you submit your map reduce job. So you have to do the configuration for the job and then submit it, and then you go back to step 2 if the output is not what you are expecting, and then retrieve data. So this is an iterative process, just like you do any program, right? You write a program, you run some tests, the output is not fully correct, you make changes to your program, run it again and see whether it's correct. So you have a bunch of test cases to make sure your program. The same thing is true here. Only thing is here you are doing it with the cloud, and this one not on your laptop. So this is just to show, I have already talked about it. So just a word on chaining. So chaining means you have one job, map 1, reduce 1, the output goes to map 2, reduce 2, output goes to map 3, reduce 3. Now this is done by something called the job conf object. So all of this, there are abstractions, there are interfaces in Java to write it. Nowadays you can also write it in Python, you can write it in C++. Almost every language is supported by Hadoop Map Reduce. So chaining examples, some of these have to be done using chaining single source shortset problem, page rank, graph property. So the above problems cannot be done in one iteration. This means several map reduce space have to be chained to solve. So you may have a chain and they iterate. That's also possible. So let's come to the summary. Additional features such as pipes and streaming. So typically a Hadoop runs on a Linux environment. I don't know how many of you are comfortable or familiar with Linux environment. So that's what it typically does. If you want to install it on Windows machine, typically you install a WSL or a virtual machine, which is a Linux machine, and then you install on that. If you are familiar with C++ or Java, it is not very difficult to understand. Of course, if you want to use advanced features, then you have to learn. Much easier than using a DBMS for some jobs where the data is in free format, more of this. Okay, so I'm going to stop here. And tomorrow, we'll see an application of using MapReduce for substructure discovery, which has been done by one of my master's thesis students last semester. So we'll discuss that and then wrap it up. At least that will give you an idea of how to use MapReduce for a complex algorithm. Thank you very much. I will see you tomorrow. I think there's only 1 hour of lecture tomorrow, followed by break, followed by exam, and followed by something else. I don't know what it is. So ma'am is already here. I knew that. So I wanted to make sure before she comes, I'm done.